So thank you for the introduction. I think I will be the only single speaker from university today. Usually in conference, it's the opposite, but it's not a problem. I will speak about simulation of Pelton turbines. Mainly, we are looking at the performance of the Pelton turbine, but mainly at off-design operating point. I will explain why in a few minutes. So in our group now, so we come from Valais here at the southwest of Switzerland. And we have, since 4 years, a consortium agreement, which is called the Hydro Alps Lab between industrial partners. So there is Alpic mainly, one of the biggest one partner, because it is the owner of several power plants in Switzerland. And we have also the operator of the power plant like hydro exploitation. And in this lab, we mix data analysis, on-site measurement. I will show you an example later, lab experiments, and numerical simulations to challenge hydropower plant regarding the electricity market change since 10 years. So we focus mainly on prediction and monitoring of power plants. And at the end, the goal for the industrial partners is to improve the flexibility, the durability of their assets in the world. So as I think you are maybe not familiar with the electricity market and the requirement for the electricity network, I just put this graph to explain why we are performing such simulations. So nowadays, you have the penetration of new renewable energy like solar panel, wind turbines, and so on. And to maintain the balance between production and consumption on the electricity network, you need to have what we call time to restore frequency, since the frequency is 50 Hertz in Europe, and you cannot have a gap from 200 millihertz between this 50 Hertz. So there are requirements for frequency containment process or frequency containment reserve. It means that when you have one unit that is stopping, you have less than 30 seconds to reach the power you sell to the market and to restore the frequency. So you need to act quickly. And at the moment, we have battery, we have gas turbine, but if you want to have something that is, I would say, clean in terms of energy and carbon impact, hydropower is one of the biggest resources that you have, since we can start a power plant in less than 1 minute or 2 minutes nowadays. So in Switzerland, we have one of the most powerful power plants that is 1.8 gigawatt that can be started in 3 minutes. So regarding the market, in Europe, 30% of the storage power plants, that means a power plant with an upper reservoir where you can store water during weeks or months, are equipped with Pelton turbine. I will explain later what are these Pelton turbines. And the main advantage of such Pelton turbine is that if we look at the efficiency regarding the discharge range, we can have a high efficiency. So this is the green curve here. So we can maintain more than 80% of efficiency for a discharge range from 20% from the nominal discharge to 100%. So if you compare to an engine, it is quite higher, obviously. So as I don't know if you are familiar with Pelton turbine, this is a very simple machine. It's like water wheel. So it means that you have water that is coming from a per reservoir through a penstock, so it is a big pipe. Then here, the flow is coming on a Pelton wheel, so kind of water wheel. And the wheel is rotating, and the water is released in a channel downstream. And here you have what we call a needle. It is kind of valve that can regulate the discharge through the machine. So how it works, it's a working principle is quite simple. So you have water that is here and is coming. So this is the needle, and you can pilot the opening here. So you have the discharge that can be changed, and then you impact the bucket here. So this is what we call the bucket, and the flow is divided in two water sheets and is released in the downstream channel. And so the power of the power plant is proportional to the discharge and here to the head. And obviously, as you want 50 Hertz on the electrical network, this is the Pelton velocity that is fit to have 50 Hertz on the electrical network. So an example, so this is what we have at the lab. So it is a very small Pelton runner. It is 15 centimeters of diameters, but as it is very small power, we can do a lot of things with such device. So here you have the needle where you can pilot the stroke of the needle to adapt the discharge. And here it's a photo where you have the water jet here impinging on the bucket and the runner is rotating. So this is the basis of Pelton turbine. So it is very simple. And now we will move to our test case. Our test case is a Pelton turbine with 6 injectors. So you have 6 jets reparted over the Pelton wheel. The power is 7 megawatt, and the nominal head, I will become on this point later, is 287.5 meters, or water column meters to be precise. The nominal discharge is 5.8 cubic meters per second, but the minimum discharge for which the power plant is qualified is 0.15 cubic meters per second, which is quite low. To adjust the discharge, in fact, as we have 6 injectors, we can close 5 of them and use only 1. It's why there is this 6 injector is to have the larger operating range or larger discharge range available. Why we want such a large operating range is because this power plant is located not so far from the source of the Rhone River in Switzerland, and this is the flow rate of the discharge at the intake of the power plant over the years. So here is the months over the years, and here is the discharge. You have the maximum value in blue. In green, it is the average value, and in black, it's the minimum value. So you can see that we have a very low discharge during winter's period. It's because it is the first power plant downstream the Rhone Glacier. So during winter, we have only snow and very low rain in the region. So the discharge is very low. But during summer period, you have glacier melt. So there is a lot of water, mainly due to climate change today. And also you can have some storm with a lot of rain. So you can have such high peak of discharge. So you need to have a power plant equipped with turbine with a large discharge range. In this project, even if we have a large range for flow rate or discharge, they want to increase more the flexibility of the power plant. To do that, we do not have a reservoir for this power plant. It means that we cannot store water and produce electricity later on time. But there is what we call the settling basin and the forebay tank. It is a basin where there is decantation. It means to avoid to have particles like quartz inside the water, because if you have quartz, I have not said before, but the water jet is more than 70 meters per second. So if you have particle quartz that impact the bucket, you have strong erosion, and then you need to change the water wheel. So on some power plants in Switzerland, they change the water wheel every 2 years due to erosion by particles. So usually you have this kind of settling basin, but in this case, we would like to use this settling basin as a storage reservoir for small storage reservoir to adjust the power for what I presented before, the frequency containment result. It means that produce electricity during 15 minutes, not more, just to allow the frequency to stay at this 50 Hertz. And we also plan to use the upper part of the address tunnels. So as I explained before, the power of a Pelton turbine is proportional to the discharge and also to the head. And the head is only the difference between, in altitude, between the water level at the top of the intake and the Pelton runner located downstream. So we want to use these two storage reservoir in addition, but if we use the settling basin, it means that there is no decantation, so we increase the risk of erosion of the Pelton turbine by particles. If we use the upper part of the address tunnel, we will make face to a phenomena that is called falaise effect. Falaise effect is something that is quite simple. Here we have on the vertical axis, it is the hydraulic efficiency. And at the bottom is a kind of dimensionless velocity. This is the ratio between the rotational speed, U, of the unit. And here, for those that follow some course in fluid mechanics, it is just the jet velocity. It's a Torricelli formula. So maybe for some of them, you remember that. And it is proportional to the head. So when we decrease the head, we increase this number. So we move to this direction. By moving to this direction, what it means is that you have a water jet, you have a Pelton wind, and as remember, the Pelton wind, the rotational speed is fixed because it depends on the frequency of the electrical network, 50 Hertz. So if the jet velocity is decreasing because the head is decreasing, in fact, a part of water is not reaching the bucket. So at one moment, a part of water is not working to produce energy. And you have this strong drop here in efficiency. And the main challenge is, are we able to predict this drop and the location of this drop regarding this dimensionless velocity? It is quite challenging. The other point is what I say, erosion. So this is a picture from a power plant. So you can see that this is a bucket, and this is normally what we call the splitter. Normally is a very sharp geometry. And obviously on this picture, you can see that it is rather flat. So the efficiency decrease. And we know from different experiments that due to the flatness of the splitter, the erosion of the inner part of the bucket, the efficiency is decreasing. So here is just some examples that we see that the efficiency can decrease by 3 to 5 percentage. So now for the owner of the power plant is to know what will be the efficiency of the runner, and if he has 6 months or 2 years to change the Pelton wind. So it is linked to kind of predictive maintenance, this challenge. So with Particleworks, we will try to simulate these two cases. So the falaise effect and the drop in efficiency due to erosion of the main splitters of this section here. And to do that, we perform numerical setups. So you have here the main information regarding the simulation and the setup. And we have limited the current number to avoid crash of the simulation. And in the computational domain, we have had this plane to simplify the geometry, but this plane has the role to shield and to protect the jet from the I would say the jet upstream. I will show you later what is the impact of this shield. So yeah, I think that regarding the setups, nothing is very specific, and we get some results. So this is on the left. You have the results for the Pelton turbine without the shield, so without this plane that protects the jet. And what we see is that if I follow this jet here, in fact, we have the jet that develop, and part of the jet is impinging this jet before it impinges the runner. And so we have a deformation of the jet, and the efficiency is not well computed. If we add the plane, we increase the efficiency, and we match the experimental data. On the right, it is an image more or less at the end after 2 runner revolution of the particle inside the computational domain. So at the end, we are around 12 millions of particles. And maybe the most important thing when we compare simulation or when we use software is to compare with experimental data. So it is the same graph than like before for the falaise effect. So you have the hydraulic efficiency here. You have the dimensionless velocity here. The stars are the result from the computation, the cycle as a result from the on-site measurement we perform by ourselves. So we measure the efficiency on-site. And this is the theoretical curve in dot line that I showed before. So you can see that the falaise effect is, in fact, arrive more faster than expected theoretically on the power plant, and that Particleworks is able to capture the tendency. And also, for 2 points, the efficiency is well captured. At the best efficiency point, we have a gap around 10%. And one of the main reasons is, as we perform this simulation of a small GPU, we were limited by the size we can set for the particles. So we expect that by decreasing the size of the particle to 2.5 to maybe 1 millimeters, we will improve the result for the best efficiency point. So, but for us, this is a very good result, because if we use finite volume method, we were not able to capture this falaise effect, in fact. It is shift to the right, but it is strongly shift to the right. And now I will focus on the erosion results. So for the erosion results, what we did is quite simple. We have a bucket here. We focus on the splitter at this location, and we remove part of the splitter. So instead of having a sharp edge, we have something that is flat. Obviously, in reality, it's not flat, perfectly flat. It's wavy surface, but for simulation, it was easier to have a flat surface. And once again, we compare to the literature. So in some books from Zhang, we have the relative loss in efficiency due to erosion. And erosion is given by the size of this flat surface compared to the width of the bucket. So when you have approximately 2% of flatness, I would say, you lost more or less 1% in efficiency compared to best efficiency point. And once again, the stars that represent the simulation with Particleworks fit quite well the curve in the literature. So this is a result that we can reach with finite volume method, but with Particleworks, we have slightly better results. And also, we get the result in shorter time. So I will show later, I think, at the end of the presentation, we will have the title of a publication that is in open access. So if you are interested, you can read the paper. And in the paper, we gain some figure regarding the time we gain using Particleworks compared to finite volume method. So I can say that for the full Pelton runners that I showed before, we perform now 2 runner evolution in less than 24 hours, whereas with finite volume method, it is more or less not possible, or it takes 1 week. So just to give you that we have a factor of 7 between the two solutions. So the conclusion, and there is 3 points. First, we are able to capture the shape of the drop in efficiency due to falaise effect. This is, I would say, maybe quite new for the community. And so not a lot of people try to capture such a drop in efficiency before, so this is very good result. Is why also we publish the results. And we also capture accurately the drop in efficiency due to the erosion of the main splitter compared to experimental data and literature. And compared to previous attempt with a finite volume solver, as I say, the results are strongly improved, mainly for the falaise effect, and are encouraging. Is why we decide to buy a license of Particleworks for a new project. This will be the end of my presentation. So we are involved in a large European project. It is a Horizon fundings. There is more than 20 partners in this project. And in this project, we are focusing on this kind of workflow. At the end, the main idea of the owner of power plant today is to go to digitalization and digital twin. But for that, they need data. And one way to get data is to perform a 3D simulation to have a map of the power plant. So, for instance, you can know what is the effect, what is the impact of falaise effect of your power plant. So this is important. You can know what will be the drop in efficiency due to erosion, and you can put all this data in a database and then exploit the database to say, okay, in 6 months, maybe we will have to change the runner or not. And you can plan the maintenance in a better way. This is the idea behind this project. There is also other idea like performing experimental model measurement during the operation of the power plant and so on to see if there is development of cracks and so on. So this is a big project, and we expect to have good results with Particleworks inside this project. So thank you very much for your attention. I expect I was being quite clear regarding this topic, and if you have any question, I'm pleased to answer. Thank you.